Hello everyone, thank you very much for joining this session. I am Syed Ghazanfar Abbas. I am a PhD student at the Purdue University. Today I want to introduce our paper SAIN, Improving ICS Attack Detection Sensitivity via State-Aware Invariants. So starting with the background, what is a PLC and how do remote attackers use it to perform ICS attacks? A Programmable Logic Controller is a real-time rugged computer embedded with control program that controls and monitors the physical process. That's why it's commonly used in the critical infrastructures such as water treatment plant and power stations. The PLC program execution involves three types of variables. Sensing variables that are updated with the real-time sensor data connected with the PLC. Configuration variables, these hold the process settings. And the actuation variables, these define the control signals which the PLC send to the actuators. Moreover, the HMI also updates the PLC variables. HMI serves as a crucial interface between the human operators and the PLC. However, the same accessibility may also serve as a vulnerability, providing attackers a point of entry to control the physical process using the PLC variables manipulation. Many real-world incidents illustrate that PLC variable attacks can lead to catastrophic consequences. For example, during the incident at Florida water treatment plant facility, attackers manipulated the configuration variables to increase the chemical dosing. Similarly, the black energy attack compromised the power system by manipulating the actuation variable. To detect PLC variable attacks, prior state-of-art defense methods use invariants, which define the relationship between the PLC variables and their value bounds. The process of invariant checking involves two key steps. First, invariants are generated by applying data mining techniques to the historical data traces. Second, these invariants are then used to monitor the real-time PLC variables data to detect violations. For example, consider a simple invariant that defines a range from the 0 to 1500 for a variable in an ICS process. If an attacker manipulates a variable above than that threshold, the invariant detects this anomaly. So this is a very simple invariant. In reality, invariants are quite complex. Despite their success, we notice that the state-of-art techniques often define an invariant as a property or a behavior that must true throughout the entire operation of an ICS. And as a result, some invariants may set loose bounds of the variable values to hold throughout the ICS operation. We observe ICS process is naturally partitioned into a set of states, ensuring that the operation of ICS in each state is completed before the system moves to the next state. Based on this observation, we found that the value bound for an invariant may vary depending on the specific ICS state. This slide illustrates a comparison between a state-agnostic and a state-aware invariant bounds. The state-agnostic approach set a global bound for an invariant. In contrast, the state-aware approach established invariant with tighter bounds specific to each ICS state. So we propose SAIN for deriving the state-aware invariants to improve ICS attack detection sensitivity against stealthy attacks. At a high level, SAIN identifies the states that are defined and implemented to control the ICS operations. From these identified states, SAIN determines the condition which include the sensing, configuration, and actuation variables in the PLC that must hold under each ICS states and converts them into the invariant templates. SAIN then quantifies the invariant templates by leveraging ICS data traces partitioned by the state to set concrete bound values in these invariants. Lastly, to enforce the state-aware invariants, SAIN has a runtime monitor that validates PLC invariants upon receiving external requests through the HMI. Now let's look at look at each of these steps. So, starting with the first step, ICS state identification. Our key observation is that PLC functions as a finite state machine running among predefined states in accordance with the control flow of the PLC program. From this observation, SAIN extracts ICS states from the PLC program. SAIN first generates an intermediate representation of the PLC program. It then builds an FSM model of the PLC code, mapping out the behaviors and transitions of ICS within and across states. After identifying the ICS states, SAIN extracts the state-aware code-level invariants, creating both intrastate and interstate invariants. In intrastate invariants, it captures the unique properties and behavior of each specific state with two main types: single variable invariants, which define that allowable value range for an individual variable, and the multiple variable invariants, which encompass a set of related PLC variables along with their respective value ranges. Additionally, SAIN leverages state transition conditions to derive interstate invariants, which are basically the rules that confirm the validity of transitions between the ICS states. After identifying the code-level invariant templates, SAIN quantifies them with the concrete PLC variables value bounds. We noticed that the system-level ICS data traces encompass all benign operations of the ICS under all ICS states. Therefore, SAIN partitioned the system-level data traces into state-specific data traces according to the state transition conditions. SAIN then quantifies the unresolved invariant templates with the state-specific subtraces, assigning concrete PLC variable value bounds. Finally, SAIN enforces the state-aware invariants using a monitoring agent, smonitor, implemented within the PLC runtime. For a remote PLC variable update request, smonitor leverages the current state to check the invariants under that state. It first verifies the request against single variable invariants. If the request passes this initial check, it then evaluates the request against the multiple variable invariants. If the violation is detected, smonitor denies the variable update request. We evaluate SAIN's security and performance aspect on the two ICS test bed. First is the manufacturing plant, Fisher Technic manufacturing plant, and the second test bed is the Tennessee Eastman chemical plant simulator. We performed the 17 attacks on these test beds. Our attacks align with our threat model. We exploit the HMI and send malicious variable update requests to the HMI. Our attacks encompass sensor variable manipulations, false configuration injections, and malicious actuator commands. So in terms of results, SAIN leverages state-aware invariants with tight bounds to detect and mitigate all 17 attacks. SAIN detects 7 attacks with just single variable invariants, and 10 attacks it used multiple variable invariants. In contrast, the state-of-art methods detect 35% of those attacks. We observe that the state-of-art methods prevent only those attacks where the invariant derived from the system-level data traces are violated. Moreover, SAIN protects the plants on average with a false positive rate of 2% and the runtime overhead of 3%. So I would like to introduce a case study where a remote attacker targets a manufacturing plant to deliberately cause a collision by dropping a workpiece. The setup includes a web-based HMI on the left side of the screen, accessible to the attacker, and the Fisher Tech manufacturing plant controlled by the PLC on the right side. So the attacker objective is to manipulate the variable with a benign value. He continually monitors the plant states on the HMI, and once it reaches in a certain state, it manipulates the value with a variable with a benign value that causes collision on the plant. SAIN detects this attack using its state-aware invariants. So let's summarize the key points. Existing ICS invariants are state-agnostic, leading to the loose bounds and detection variant. State-aware invariants achieve tighter state-dependent bounds and improve detection sensitivity. SAIN enables offline generation and runtime enforcement of state-aware invariants with high detection accuracy and low overhead. This is the end of my presentation. We would like to say thanks to our sponsors NSF, CNS, ONR, and Cisco. Thank you very much for listening. I am happy to take any questions.